Alon Dogon. He will talk about stability and approximation for high-rank lattices.
Thank you, Tatiana. Yeah, I want to thank the organizers also for inviting me, but mainly for organizing this event. Yeah, I've been working on stability for a long time, and I really am enjoying this celebration of this topic. It started out, yeah, it's been really amazing to see it develop, but I really, today in my talk I want to kind of, I decided to do more of a high-level talk, so it won't assume that you've been in the other lectures in this talk, so maybe the first few slides will be boring for some people, but I really do want to kind of emphasize what I find as the most pressing questions that still need to be addressed, and that it's kind of frustrating that we still don't know an answer to them, neither a no answer or a yes answer. And yeah, so I kind of want to, for this talk, focus on a setting of higher rank lattices. I won't assume you know what that means, but really, I mean, this is a topic by itself, and I kind of want to exemplify how stability and approximation plays out in this setting. Right, but let me kind of start with reminding what do I mean by stability and approximation, right? I mean, this is one of those conferences where this notion will be defined again and again and again with different definitions, right? But that's the point. We are people from separate topics. We all view this separately. But let me kind of give a relatively global picture that I learned from Alex. Right, so what do I mean by a metric approximation of a group? This was something that came up in Gunala's talk. And in this setting, I kind of want to start with the most general case. The most general case is where I'm approximating a group by a general family, denoted Gothic G, a sequence of groups, usually taken to be finite symmetric groups or finite unitary groups, but you could do linear groups over finite fields and many different things. But the important data I need about them is a specified sequence of metrics. Today we will kind of see how this specification is particularly important. So G and Dn are my groups I'm trying to approximate by. Then throughout the talk, gamma will denote a countably infinite group. I mean, it's not important to assume it's countable, but think of a discrete group. And I'm saying that it's approximated by this sequence if you have a sequence of maps, phi n, from your infinite group gamma to Gn, which are not necessarily homomorphisms, but are asymptotically multiplicative with respect to the metric. Right? Just a sequence which becomes more and more multiplicative on the one hand. Right? Such sequences always exist. I can just take trivial sequences. However, the non-trivial condition is that I have some form of separation. And to capture separation in full generality, kind of a weak form of separation is simply to assume that the images of non-trivial group elements are always bounded away from the trivial element in Gn. Right? So this is what I call a G-approximated group. Now, stability is kind of a twin definition where here, this is an existence definition, right? We wanted the existence of some asymptotic homomorphism. Stability asks something for every asymptotic homomorphism. Stability asks that every asymptotic homomorphism is in fact close to true homomorphisms, right? In this setting. And the example that we've seen the most of, and is the most important example, is when you take Gn to be the family of finite symmetric groups and consider the normalized Hamming distances on them, right? This was the topic of Gunala's talk and also the topic of Henry's talk this morning. And in this regime, you get what's called sulfic groups. These are the G-approximated groups, and permutation stable groups. These are the G-stable groups. Any questions about this? Because this is like the two main definitions. Please ask questions. I mean, I kind of am trying to give you a picture of the current state of the art, and so it can be confusing because there are various different regimes you should be considering. All right, so we saw the sulfic example, but now let me, most of the talk is going to focus about unitary groups. so simply n by n unitaries, equipped with various different metrics. These will be my GN. So previously we were talking about approximate actions, and now we're talking about various different notions of approximate representation theory, right? And here the theory kind of, is richer in some sense, where there's more than one metric that is natural to consider for measuring distance between matrices, right? For me, and the thing that came up in this conference already is what's called the normalized Hilbert-Schmidt metric, right? All my metrics are defined by unitarily invariant norms, right? So this formula, like to define a distance between two unitaries, I simply define a norm on matrices, right? And the normalized Hilbert-Schmidt norm is simply treating your matrix as a n-squared dimensional vector and taking its Euclidean norm, but then normalizing importantly by a factor of square root n, right? This is captured by this formula. Okay. In this regime, the question of approximation is called finding hyperlinear groups or con-embeddable groups. This is a notion that originally arose in the theory of von Neumann algebras, as you might have heard in Christine's talk. I will make the connection a bit later. But the stability question is the one of Hilbert-Schmidt stability, which was introduced by Itama. Right? You're asking like matrices which almost satisfy some relation. Are they close to truly commuting matrices? Right? Itama explained why for the Hilbert-Schmidt norm, Glebsky proved that this is true. All right, but another norm which appeared was the operator norm, right? Which is more like an L infinity norm. This 2 norm I think of as an integral norm, and the operator norm I think of as like a worst case norm, right? And they are very different. For example, projections can be close to each other in the 2 norm, but they are always far from another in operator norm. And just to clarify the kind of the lingo, which is part of the difficulty of the subject, here approximated groups are called MF. This is something that will come up tomorrow as well. These are called matricial field groups. And by the way, even MF group doesn't have a singular meaning. It can mean 2 different things, which one is, we will get to this. Yeah. Anyway, so for me, an MF group is one which is approximated in the operator norm. And the stability has several names. I think it's also called matricially stable, but I will, for this talk, just say operator norm stable. Right? And what Itama explained was that even in this simple situation, this von Neumann's question of almost commuting matrices already exhibits a different behavior, right? It's Z-squared is Hilbert-Schmidt stable, but not operator norm stable. Now, a norm which didn't come up yet, but is, you will see, interesting to consider, is basically take this 2 norm, first of all generalize from taking a 2 norm, generalize to taking a P norm. These are called shatter norms. These are kind of analogs of LP norms for matrices. But more importantly, look that here I have a factor of 1 over n, and here this factor is missing. Okay? This makes all the difference in the world, as we'll see in a bit. So basically, if you put 2 here for P, then this is the Hilbert-Schmidt norm up to a normalization. Okay? Okay, these are kind of the 3 classes that I would want to consider and tell you what we know about them. Now, first of all, I do want to repeat the observation that these are metric notions of approximation, but when your group is algebraically approximated by finite quotients, which are residually finite groups, then it will satisfy any one of these approximations you might want. Right? So residually finite groups are G-stable for any one of the families I described, and these families a priori are not clearly related to each other, except for the case of Sophic and hyperlinear groups, where sophicity implies hyperlinearity. Right? The basic idea is if you have an approximate action, you get an approximate representation by looking at functions on the action. That will play well and show that Sophic groups are hyperlinear. So this is, in this conference, when you hear hyperlinear groups, you should in particular think of Sophic groups. This is the connection. And, all right, the question that everyone's interested in is, can we find non-approximated groups for these various families? Now, the key observation that came up in basically all the talks before, which I attribute to Glebsky and Rivera, but also Aljantsova and Palnescu, it's kind of present in both works, that if you have a group which is both residually finite, so algebraically, not residually finite, so you know it's not algebraically approximated, but on the other hand, it's G stable, then it's not G approximate. Right? And the reasoning is simple. As I said before, G approximation is an existence statement, so you can in particular imply the object which is guaranteed to exist in approximation. You can apply stability to it, which asks something for all asymptotic homomorphisms, and the separation would exactly mean that the resulting homomorphisms to Gn would separate your group algebraically. So this observation is kind of a bit simple, but it's kind of playing off a rigidity property against a loose approximation property and upgrading it to an algebraic approximation property.
You don't RF, you want to okay, it's not necessarily RF in general, right?
It will be because all my groups are either, all my approximating groups are either finite or linear, right?
Okay,
it's
so
true that in the case of unitaries, you need an extra small ingredient which says that finitely generated linear groups are residually finite. This is an important thing. And also in Henry's talk, right, he advertised a quantitative version of this for the case of sophicity. You actually can do, so for example, in the linear setting, this is maybe more complicated, right? Because residual finiteness is about separating by quotients. You might ask about separating by representations, and those are, you would also need to quantify how those are related. Anyway, but in all the things I consider, this is true. Yeah, okay. So the big three, right? All these questions, I think, respectively from different communities, would be considered holy grail problems, right? But let's start with the most famous one, the Sophic question. This is first attributed, so this, I mean, many people know, but this is still a funny story, right? Gromov defined this notion, he didn't give it a name, he defined groups whose Cayley graphs are somehow approximated statistically, and Benji Weiss studied it in relation to entropy theory and cellular automata over groups, and he gave it the name Sophic because Sophie in Hebrew means finite. So it's unfortunate because in Hebrew I cannot speak about Sophic groups without confusing people, on WhatsApp at least. But yeah.
The precise story is that he thought about calling it finitary because it's like finite, but he said that finitary mathematics is full of finitary, so many. So in this sense of humor, he called it Sophic. There is no word like that in Hebrew. In Hebrew, you say Sophie, not Sophic. Sophic sounds maybe Greek or something, and it was picked up by everybody, and now.
Yeah. But let's agree this is a good name. I mean, except for in Hebrew. So it's a nice name. It's catchy, right? And but let me really mention, like, why did Benji or even Gromov originally consider it? It was because of symbolic dynamics, actually. So there is a notion of cellular automata over groups. If you've heard of Garden of Eden, this is a particular case of it. And there's like an open problem called the Gottschalk conjecture about whether every cellular automaton which is injective is necessarily surjective, and that is open, but Benji and Gromov proved it for Sophic groups. Later, this entropy notion was realized to be much more like universal than originally imagined by Louis Bowen, which basically, for Sophic groups, you have some notion of entropy theory for dynamical systems, which is very important. But also, of course, this directly relates to L2 invariance and other approximation theorems, like generalizations of Luke's approximation theorem and so that finitary approximations really are useful. So it is an important question. Can you always do that? Of course not, but we don't know. All right, hyperlinear groups, right? In this setting, we are almost in the Sophic setting, but now you're approximating by representations. And this was originally, in some sense, stated by Kohn. Right? In Kohn's celebrated result on the the classification of amenable von Neumann algebras, he kind of reached this property of conembeddability, which basically is hyperlinearity for von Neumann algebras, and asked, okay, whether every von Neumann algebra is conembeddable, right? As was mentioned in Christine's talk, but there is still a more specified question, which is whether every group is conembeddable. The algebra arising by a group is conembeddable, and that is still wide open. Both these questions are wide open. Right, and of course it relates to quantum information theory as well, but the third question, which I think has not been mentioned yet, is the MF problem of Blackadder and Kilpel, which appeared in their papers. Actually, this notion is mostly motivated originally by the classification program of C-star algebras. It's somehow an important thing related to quasi-diagonality as well. But I mean, that was their interest. I'm not sure even if they explicitly asked this question, but people quickly realized we don't have an example of a non-MF C-star algebra. But I would say that in recent years, there's been also a new source of interest in MF algebras coming from the world of strong convergence and strong forms of spectral gap. I will maybe mention that a bit, but you should really look at the recording of Michael McGee's talk from the last conference, where kind of this connection has been explored more. But there are many other related questions coming from there as well. Right, now I want to say, what do we know? Any questions before?
Just a comment. Gromov has a name, but it was not a good one.
What was it?
Initially subamenable group and initially subamenable calligraph with for two fields.
I see.
Yeah. So,
Okay.
So it was unfortunate.
Yeah, because it would imply that it kind of says that the Sophie groups are locally embeddedly amenable, right? Which is not true.
No, he did differences, but just used the same kind of difference between group and calligraph. So
yeah. Okay. Unfortunately, for stability, we don't have good, such brilliant minds to come up with good names, so we're stuck with the current terminology. Sorry. No, sorry, of course, we have very brilliant minds working on stability, just that the naming problem is still very open. Yeah, I should correct. Sorry. But okay, now let me now we're getting to some mathematics, okay, and not just speculation. I want to tell you what the moral of my talk, and you can forget everything else, is that these questions are still very open, but we have very specific candidates, which regardless of the general question, it's still extremely interesting to decide for them specifically whether they're approximated or not. Okay, and the examples are kind of hidden here, but let me call them in general central extensions of higher rank lattices. I will give another example on the board in a second, but let me read out this theorem, which is kind of a combination of works of several people. So we have an example called Eladic Deligne central extensions, which, how do they arise? They arise as finite central extensions, gamma tilde, right? You have a short exact sequence here with a central kernel, which is just a finite cyclic group, where L here is a prime, by the way. It's not clear, but L I'm thinking of as a prime. And the base group here will be a lattice in a symplectic group over the Eladic integers, right? I don't want to say exactly what lattice, but I don't think it matters too much as well. And what we know about this mysterious gamma tilde group is several non-approximation properties, mostly in the third category, right? Recall the third category was these unnormalized p-shatter norms. So by now we basically, we basically know that this group gamma tilde is not approximated in any one of those p norms. Okay, but let me maybe kind of illustrate the history a bit here. The first result in this direction was done for the unnormalized Hilbert-Schmidt norm, so p equals 2. This is Schatten 2 norm. It's also called the Frobenius norm. And there, de Chiffre, Glebsky, Lubotsky, and Thom pioneered an amazing method for proving stability. I will mention it in the next slide, which relies on cohomology vanishing. Right? So somehow this was the first time where we had some systematic tool for proving stability for non-amenable groups. Right? Like if you imagine Hadwin-Schulman and Becker-Lubotsky-Thomas, the tool you use to prove stability of amenable groups, in the non-amenable setting, this is basically the only generic tool we have. But they did it for p equals 2, and then Lubotsky and Oppenheim kind of extended it to larger and larger symmetric intervals around 2, depending on the prime L. So to get a large interval here that is not approximated, you would need to take a large prime, right? And recently with Benny Bachner and Alex Lubotsky, we did the edge case of p equals 1 as well, which turned out to be much easier than originally expected. But more impressively, the ultimate result is an upcoming one of Bader cubed. So Uri Bader, Jacquet Bader, Sal Bader, and Roman Zauer, who I hope will say maybe something about this. But okay, this work is still upcoming, but it should be a corollary that the previous groups I considered, a single one of them, the L-adic central extension, is not approximated for any p-norm, and moreover is stable for any p-norm, between 1 and strictly less than infinity. Right? So this is kind of the ultimate example for a non-approximated group in p-norms. And again, as I mentioned, the techniques here are cohomological in nature and connect beautifully to this new study pioneered by Uri Bader and Roman Zauer of higher property T. Right? Let me kind of illustrate why this is nice, because you might complain that the previous example was a bit obfuscated, but let me give you a somewhat simpler example. You can take the group gamma. Instead of a lattice in a p-adic symplectic group, you can take it in a real symplectic group, right? So I can take gamma to be SP to G of Z. So simply symplectic lattices, integer matrices which preserve a symplectic form. This group will have a topological central extension gamma tilde, in this case with kernel Z. But you can actually do it with finite kernel. You can deduce it for some finite kernel. And in this context, if this group is stable, then this group is not. In this context, we know that these mystery central extensions, which come from topology, are not approximated as well in the p-norms. Again, by cohomological vanishing results, which are harder for real groups. All right, but now I kind of want to give you a proof, not of the hard result, but just to explain why actually the original result of Glebsky, Lubotsky, De Schriffel, and Thom implies already that the group is not approximated for p less than 2, including 1, by a very simple argument. But any questions before I do that? All right. So let me explain why when you have such a situation, and now you can kind of forget that you have any specific lattice here. All I need to assume is that the group gamma is residually finite, and gamma tilde is a central extension with a finite kernel. So I'm going to prove that if this group is 1 norm approximated, then it's also 2 norm approximated. Is it clear what I'm doing now? Okay.
The kernel also, the middle group can't be residually finite, right?
Yes, that's true, sorry. And plus, no, that's not important. I'm going to show by some argument that if you have a residual, let me erase this because this is not the assumption I need. So I assume that I have gamma is residually finite. Then if gamma tilde is 1 norm approximated, it is also two-norm approximated, without assuming anything else. Yes, it is two-norm and in fact p-norm for any p greater than 1. Right, and then clearly the L1 case would follow from the previous hard work. So what is the argument? Okay, let's call the generator of this kernel J. So J is just an involution. Now what do we know? We assume that gamma tilde is one norm approximated, so we have some one norm approximation phi n. Right? Okay, so far so good. Now, the important thing, by the way, this is not an arbitrary asymptotic homomorphism, so the thing we know is that phi n from gamma tilde, so is one norm asymptotic homomorphism, and at least we know that phi n separates J from the identity. So, greater than 0. Right, because we assume that phi n approximates gamma tilde. In particular, it separates the non-trivial element J. Okay. But we also know that phi n of J is almost an involutive unitary, right? And then there's kind of a mini stability lemma which says that if you have an almost involutionary unitary, or an almost order 2 unitary, then it's close to a unitary of order 2. Right? So there exists, this is this lemma, for every u there is some v, such that v squared is indeed 1, and the defect of how far u is from being order 2 bounds the distance between u and v. And this is true in any invariant norm. Okay? This is kind of, you can prove it by SVD. All right, so what do we know? So this phi n is close, or we can basically replace it with an order 2 unitary. Right? But how does an order 2 unitary look like? Just diagonalize it, right? And it will have some trivial eigenspace and potentially some non-trivial eigenspace. Now it has to have at least some non-trivial eigenspace, right? Because it's not the identity. So it has at least one. But once your unitaries of this form, you have some -1 on the diagonal, it is at least square root 2 far away from the identity in any p norm, right? In particular in the 2 norm. So this thing is separated in 2 norm, right? So on the one hand, I managed to separate the kernel J, and on the other hand, I assumed gamma is residually finite, so it's 2 norm approximated. So I can take different parts, one to separate J and one to separate the quotient, and get that gamma tilde is 2 norm approximate. Right? So this settles immediately the 1 norm case. Now,
sorry, so
yes.
really what you used about Z-mod 2 is that
It's finite.
one stable?
It's 1 norm stable, sure.
And that's it? Or
That's
also
it.
this
And
special
finite.
norm?
Now it's important, when you have an infinite kernel here, I'm not sure this argument doesn't work because you have characters which are arbitrarily close to the trivial character. Here I'm using the fact that for Z-mod 2 the characters are separate. Okay? Any other questions? Right, okay, so this is cool because this was kind of, it's an easy argument, but it's kind of refining this idea of Gleb's, of the key observation I was mentioning before, right? I'm trying to say that for these groups with a specific structure of a central extension, you can kind of refine this idea of using stability to contradict approximation. But now you can use stability in another norm to contradict an approximation in a different norm, right? And let me kind of exemplify this also in the operator norm setting. Right, but before I get to this proposition, I really do want to address a little bit this MF thing, because it took me some time to realize that there are two different definitions of MF, and they're not, both of them are open. Both, like, you have, it's not a name, strongly MF groups and MF groups, both of them, we don't know to construct an example. So it is unclear whether the Stalin central extension is MF, meaning can you extend to P equals infinity? This is a very, very interesting problem, and in some sense the most approachable one out of all the approximation problems. But I do want to advertise that there is actually an even stronger form of approximation that we don't know to contradict, which says whether there is an asymptotic representation in operator norm which strongly converges to the regular representation of gamma tilde. So strong convergence, let me kind of define it, if you can see, is that, so phi n from gamma to un strongly converges to the regular representation if for every group algebra element in gamma tilde you have that when applying this asymptotic representation, you look at the matrices you get from taking a linear combination of the unitaries you get here according to Z, and measuring the operator norm, this should converge to the operator norm of the regular representation applied to Z. This is equivalent to the condition I've written above, which is more a con-embedding form of the problem, asking whether the reduced C-star algebra, which Christine introduced as the algebra generated by the regular representation, embeds in a universal MF algebra, which is the ultra product of matrices in the C-star category. Right? So even that we don't have an example, and this is somehow a much stronger condition, should be a much stronger condition than just operator norm approximated, because even proving the free group has this properties is an extremely hard thing, which we don't have. We only know to prove. I do not.
There is no example
Yes.
for which this is not be possible to embed.
There is no example of a group gamma tilde which this is not embeddable.
In this sense.
Yes, which is a stronger, like this is a stronger property than being operator norm approximated, much like should be a stronger property, and this also we don't know to contradict. Yes.
It's a conjecture for stably finite C-star algebras. There's a tracial stably finite C-star algebras. Very general.
Yes, but in the group setting,
there's a large class of C-star algebras.
yes, there is an analog of the con-embedding problem, and this is kind of the analog of the hyperlinear group problem. But the reason is that the fact that gamma is operator norm approximated, like, says that gamma embeds in the unitary group of this algebra, but this embedding does not necessarily extend to the regular representation. This is something that is more rare and doesn't happen for any asymptotic homomorphism. So this is just an advertisement for kind of the question I consider the most approachable. Prove that for these Alin central extensions, you do not have such an embedding for the reduced C-star algebra.
Even for amenable groups.
This is very hard, yes. So Tikwisis, White, and one of the pivotal theorems in the theory of classification of C-star algebras is to prove that amenable groups are quasi-diagonal, in particular they're MF, meaning that you have such approximations for their regular representation. This is very non-trivial, and we know it for free groups, we know it for amenable groups, but limit groups and some other two-dimensional groups, free manifold groups, I think as well, but we don't know it. Even for SL-free Z, even for our linear high-rank lattices, we do not know the answer to this question. Right?
Could I ask what the reference for three manifolds is for that? Sorry.
I think it's this. So in Michael's talk, if I understood him correctly, for free manifold groups hyperbolic free manifold groups by virtual specialness, you can embed in a RAG, and there's the result of I think Hyde and McGee that RAGs do have finite dimensional representations which strongly converge, but it's still an open problem about permutations. So there's kind of the subtlety there is different, but for this MF problem, we do know like an even stronger problem. We know that there are actual representations which converge strongly to the regular one. Is that correct, Ewan? Okay, yeah. But we don't know it for high rank groups. But all those results are extremely hard, and you need to work to prove that. And I'm saying, can you just disprove that for this group? All right. And the problem here, which kind of people hit, was the fact that we don't understand well this cohomology group for representations of your group gamma tilde into an ultra product, basically an ultra product representations of finite dimensional representations. If you can say something about the second cohomology group of gamma tilde acting here by conjugation, then you should be able to solve this problem immediately by the techniques of homological techniques of the Frobenius paper I mentioned. Now, another way maybe which you can approach this MF problem is similarly to this, this proof. You can do a similar argument using the fact that J is of finite order to show that you don't need to prove operator norm stability to contradict MFness. It's enough to prove a mixed type of stability between operator norm and Hilbert-Schmidt norm. It's enough to prove that for any MF approximation or any MF, any operator norm asymptotic homomorphism, you can find a correction in Hilbert-Schmidt norm. This should be in blue. I don't think it's apparent enough, but the correction here should be in the Hilbert-Schmidt norm. Right? If this is correct, then the group still isn't MF by a similar argument. And we kind of conjecture, or we couldn't find this could potentially follow from homology vanishing for Hilbert spaces. This is something that I think is not clear yet, but should be investigated, like are lattices stable in this sense? All right, how much time do I have left?
There's a big
20
clock.
minutes. 20 minutes.
20 minutes. Okay. Now I want to kind of switch gears and talk about a separate study, which comes from the Hilbert-Schmidt setting, but any questions on the MF thing? Yes?
What is the relation between operator homomorphism and Hilbert-Schmidt asymptotic homomorphisms? So like
that operator norm asymptotic homomorphisms are in particular Hilbert-Schmidt. But the fact that you correct them to homomorphism in Hilbert-Schmidt norm doesn't necessarily say you have corrected in operator norm.
I see, yeah.
And
so
in fact,
this is a weakening of
operator norm stability. Hilbert-Schmidt stability is different. It's both stronger and weaker. If you are operator norm stable, then in particular you're correcting in operator norm, you're in particular correcting in Hilbert-Schmidt norm. And the reason I'm saying this is because Marius Dadalat and Forrest Leb, they will talk about why operator norm stability is a rare property, in particular for groups such as this, the real so the p-adic thing, I don't think we know that it's not operator norm stable because all of its cohomology groups vanish. But for real lattices, you have trivial cohomology, and that, in even degrees, obstructs operator norm stability. So you need to replace it. Okay. Now let me talk about the hardest situation, the case of Hilbert-Schmidt stability, of hyperlinearity, or the Hilbert-Schmidt norm. And this, of course, is in some sense the most desirable one because another thing you can prove is that if gamma tilde is MF, then it's in particular hyperlinear. So the hyperlinearity question is really the hardest question, and it would also imply a solution to the sophicity question. So let's try to understand what to do here. Right, so there are problems with implementing the cohomological techniques that I mentioned. The most apparent problem is that the cohomological techniques fail because the Hilbert-Schmidt norm is not submultiplicative, right? If you look at unnormalized 2 norm, then the trace norm is submultiplicative. But when you do this normalization, then you suddenly lose a 1 over n factor, right? So the correct type of submultiplicativity is captured by a mixed notion of both the Hilbert-Schmidt norm and the operator norm. But you can't apply blindly the previous techniques. And the reason is that the submultiplicativity is important to even pass through a homological question about infinite dimensional Lie algebras. But even kind of, okay, this problem is really is significant. There is a second problem, which is that all the groups I talked about, high-rank lattices, they're not Hilbert-Schmidt stable per se. There is a paper of Becker and Lubotsky which shows that property T groups, and in fact, property tau or property TFD groups, cannot be Hilbert-Schmidt stable. But the reason there is kind of because the notion is too rigid for a dimension change. So really the correct notion of stability that you should be working with here, let me define it briefly, called flexible stability. So the thing is, like, before we were measuring distances between unitaries of the same dimension, now I want to get a distance measure for unitaries of different dimension, right? So I want to extend the 2 norm distance to the disjoint union of all unitary groups at the same time. And I will measure the distance between an n-dimensional unitary and the m-dimensional unitary, where say m is greater than n, as follows. I will first take x, the smaller unitary, and embed it as a corner. So x and add a bunch of zeros, n-dimensional, m-dimensional. So I add 0 coordinates. Sorry, this is writing the definition for the distance. This will be the Hilbert-Schmidt distance between this cornered matrix and y, measured according to the larger Hilbert-Schmidt norm, to m, where m here means I normalize by m. Okay, this is the Hilbert-Schmidt. This is the Hilbert-Schmidt distance. I should mention because 2 is. Right? So in this definition, I'm just penalizing extra dimensions. So for 2 unitaries to be closed, they need to, first of all, be in relatively close dimensions, and secondly, the corner of one should be close to the other. Okay? It's, this is more similar to the definition of flexible stability as given by Becker and Chapman. Let's call this thing the generalized Hilbert-Schmidt metric, which simply means I can measure distances between different matrices. And by the way, if you forget about the extra dimensions, you exactly get very flexible stability. And yeah, this is the correct notion to work with because property T groups are not Hilbert-Schmidt stable, but they're potentially flexibly Hilbert-Schmidt stable. And the open question here, as in with the MF situation, is do we have any example of a high-rank lattice which exhibits this form of rigidity?
Is there any example of a property T group with this?
No,
Okay.
we don't have, let me be even worse. We don't have a single example of a flexibly Hilbert-Schmidt stable group which is not already Hilbert-Schmidt stable, right? And in the case of permutations, we have this beautiful work of Aryeh, Nir, and Yair Minsky, which show that the surface groups are flexibly permutation stable. And even there, we don't know whether the flexibility is needed, although Neil mentioned that the flexibility is needed in a similar problem. But yeah, this is wide open. I would expect, to be honest, that these groups that most high-rank lattices should fail flexible Hilbert-Schmidt stability. But in a second, I will explain like the most interesting case study for which I don't know the answer, and it's so elementary that someone should be able to say something about it. Right? Right. So let me kind of now switch gears and be ultra elementary. So yeah, before we were passing between the p-adic and the real world, right? Let's combine them. That would be even better. So, right, this is just the standard picture of the modular group acting on the hyperbolic plane, just because I like it. It's not, but here it will. I'm not going to consider the group SO2Z. I'm going to combine it with a p-adic analog. And what would be that? That would be the group SO2Z, where you adjoin the number half to the ring Z. So I wrote it out even here. It's 2 by 2 matrices, unimodular, which have entries in dyadic integers. Right? And the kind of important thing about this group to remember is that dyadic integers, I can view them as a subring of two different fields. One is the real field, it's dense there, and one is the two-adic integer, so this is Q2 if you can't see, and it's dense there as well. But if you look at the diagonal embedding of simultaneously looking at the real embedding and the two-adic embedding, then suddenly this is a discrete subring, right? And similarly, this discreteness and the fact, and less trivially, the fact that it's of finite covolume passes to the algebraic group. Right? So this is an example of a gamma is of finite covolume inside this topological group, and it's an example of a lattice in a product of rank 1 groups. So why does it still land in kind of my category of higher rank lattices? The reason is that I have at least two factors here, and the rank is additive. High rankness is, in this group is a bit less apparent than the one we had previously, right? Because you might at first sight say, this is so similar to SL2Z, right? And the theorem I maybe will explain a bit of the proof of, but I kind of want to really understand what it says and what it means, is that if this group is flexibly Hilbert-Schmidt stable, then we get a non-hyperlinear group, in particular a non-Sophic one, in particular a non-MF one. Right? Now, why is this interesting? To see why this group is particularly interesting, we need to kind of pass to the p-adic world, right? And in this, the point is that because this group also has a p-adic embedding, SL2Q2 acts by tree automorphisms on a free regular tree, right? There's this beautiful construction that is heavily favored by Alex, and it's an example of a Boititz building, right? Of one-dimensional, of rank 1 Boititz building, where SL2Q2, you can construct a very natural action out of its arithmetic origin, which on a graph, which turns out to be a tree. Right? And Basser theory tells us that any group which acts on a tree, we have non-trivially has an amalgamated product decomposition. Right? So what, I won't specify what is the action here, but just by understanding what is this action, you can use Basser theory, and this was realized even before Basser theory, that this group gamma is an amalgamated product, right? So going to Gulnara and Liviu's talk, of two copies of SL2Z over a subgroup B called the Iwahori subgroup, but explicitly it's just the following thing. It's just matrices A, B, C, D where B is even. All right? Now this is a bit confusing, misleading to write it in this way because there are two different embeddings here of B, but any questions about what are the groups appearing here? Because I want to kind of continue with that.
So B has some specific properties?
B is a congruence. B is an index 3 subgroup, right? B will be an index 3 subgroup. It's important it's not index 2.
Still not free.
Is it free? Probably.
Yeah, why not? I don't know.
Yeah, free.
It's free.
Yeah.
It's a free subgroup. And as Gnana,
No, with an F.
Free.
No,
It's not free. No, no. I thought
it's not free?
Okay.
No, it's not free.
Ah.
I mean, it's not a finite index in SO2Z as well. But, no, it is a finite index in SO2Z. Yeah. Anyway, this is a congruent subgroup, right? It's a finite index subgroup, which, basically, it's take SO2Z, take the quotient map to SO2Z mod 2, and pull back the upper triangular matrices, or lower triangular matrices. All right, but let me be a bit more, okay, now let's kind of explore what kind of question do we get when we ask whether this group is stable. So, the point is that we know that SO2Z is Hilbert-Schmidt stable, right? So we are landing in this constraint situation where you have two stable groups, and you're asking whether an amalgamated product is stable again. This, this appears in the paper of Gerasimova and Shepin. It's not completely clear that SL2Z is stable, but it is. Now, really I want to explain a bit more how the amalgamated product works, right? I in fact have two different embeddings of B. One I call B minus, so these are the kind of lower triangular matrices, and B plus is the upper triangular Iwahori subgroup. And you have an isomorphism between them which just switches which coordinate is even, right? But this is not the transposition. This is this is a commensurator of SO2Z. This map, taking this coordinate and taking this being even to this being even, it does not preserve SO2Z, but it commensurates it. It's exactly defined by the action of conjugation by the matrix square root 2 and 1 over square root 2 in SL2 Q2. Okay. Now, what does flexible Hilbert-Schmidt stability mean then? It means that if you have two actual representations of SL2Z, this is something that is well studied, right? Unitary representations of SL2Z, such that this diagram almost commutes, right? Where when I say almost commute, I really mean that like B plus and B minus are free generated. You can pick generators and ask these restrictions to be close to each other on the generators when you restrict and then commensurate. Right? So this diagram, right, this is the commensuration. These are the embeddings, and this is the representations. You want this to approximately commute. Is every such diagram close to an actually commuting diagram of representations of SL2Z? Right? And in some sense, I can call pairs of such representations congruence representations of SL2Z, right? Because this is another thing I learned from Alex, but SL2Z half has the congruence subgroup problem. So its representations exactly correspond to unitary representations of SL2Z which factor through a congruence quotient, albeit an uneven order. Right? So the whole question really becomes a question about SL2Z, and I really believe that it should be possible to decide this, whether it's true or whether it's not. I believe it's not true, but just to exemplify, you get a very concrete question, and it's, I think, a good question to think about. I'm happy to discuss it any more later. Yeah, thank you. There are more results I can mention, but let me kind of end here and make time for questions.
Any questions or comments?
So what is A, the group A that you construct?
Let's see, A. What is the group? Great question. It's good someone asked it. So it's again analogous to this Deligne kind of extensions. So let me explain that in fact it's a good candidate because it's not residually finite again. So you have SL2 Z half sitting inside of a semi-simple group, SL2 SL2R times SL2Q2. Now, SL2R is not simply connected. You have a universal cover here on the first coordinate. And you can pull this back to a subgroup. And here you will have infinite group. What the theorem says is that if this is flexibly stable, then this is not hyperlinear. And if you look at Deline's proof, and in fact it was noted already by Raghunathan and such, the proof really just uses the congruent subgroup property of this group. Right? I think even if you have a hyperbolic group which has the congruent subgroup property, then you can kind of show it as a non-residually finite cover. But just by the mere fact that this is the congruent subgroup property, and maybe some, basically that implies that this group is not residually finite. Right? So again, you get this Deline kind of situation, but where you need to analyze the stability of the base group and not the overgroup.
What is this written in your paper?
The fact that this is not residually finite?
No, that if this is...
It's, sorry, I'm so sorry, Did I mention this is all a joint work with Itamar Viktorovich? Did I say that? Okay. Yeah, this theorem, all I've said about Hilbert-Schmidt stability is in a joint paper with Itamar, where we can say something about asymptotic representations of this guy, as long as these asymptotic representations are hyperfinite, which maybe Itamar threw around, we do know to correct them. But that's really just a mirror fact of a theorem of Andreas and Jesse Peterson, that this group is character rigid. This tells you something about asymptotic representations which do not converge to the regular representation. Those are correctable. But really the question here is, I give you a hyperlinear approximation of this guy. Can you say it's close to congruence representations? Yeah.
And so for all these questions, I mean, in the kind of basic scheme of like stable plus approximation, you only need weak stability. Is this the case?
Yes.
Phrasing?
As I said, this only needs weak. All the things only need for approximations. And further, like in this situation, things which like really don't approximate, they are hyperfinite. Like that would converge to an amenable thing, and then that we understand. That we know to approximate, essentially by the techniques of Hadwin and Schulman, but kind of generalized to the non-amenable setting. So we give a definition called hyperfinite Hilbert-Schmidt stability. I saved you the trouble, because there are too many things. So that we know for these groups, but of course the interesting thing is about hyperlinear approximations.
Just make a quick comment on that from the MF question.
Yeah.
Just I guess tie in a little bit with some conversations we're having in the break. If you have a reduced C-star algebra that's MF, and you also know that it is has any sort of lifting property, then that automatically will give you quasi-diagonality. The definition of quasi-diagonality is having this synthetic that is reducing MF. You can take that as a definition. And that's equivalent by Rosenberg's theorem to the group being amenable. And so you sort of have this setting where you can say, if you can come up with a non-amenable group where its reduced group C-star algebra has the local lifting property or the lifting property, then you automatically have your terms on both a non-MF and non-hyperlinear group.
Wait, but you are saying if like F2 times F2 has the local lifting property, then you have...
So non-amenable reduced group C-star algebra.
Sorry?
Or the reduced group C-star.
The reduced one.
Yeah.
I see.
But that also is a second comment. This is also pretty highly advertised as trying to figure out whether the full group C-star algebra for SL3Z has MF. That specific example tends to be pretty highly advertised.
Right, yeah. The full one.
The full one.
It does not follow from the group being residually finite, you're saying.
It's not RFD. That's the interesting thing. This
Yeah,
is one of
that's
the,
true.
This is the first
Okay.
example.
I completely agree. That's also a good question.
Yeah.
Yeah. Again, in the C-star algebraic setting, you get kind of various different MF questions attached to a single group. So there the situation is more complicated, of course.
But it's the same for groups. I mean, the group being residually finite and the C-star algebra being residually finite.
Yeah, for approximation properties of the C-star algebra, residual finiteness or MFness or whatever, like it really depends on which one you're talking about, and there might be a difference from the corresponding property. Yeah.
But I'm saying the difference in terminology doesn't have with MF, right? We have for residually finite or maximally almost. We have a definition for groups and definition for group C-star algebra.
Yes.
Right? So now with MF, we have a definition for groups and a definition
Yes.
for algebra. So there is
Yeah.
no confusion in terminology. That's what I'm saying.
I see. Okay.
Questions? I have a question.
Yes.
So for this group tilde gamma,
Yes.
how it happens that those cohomologies which are needed for Frobenius stability are computed, but those cohomologies which are needed for operator norm stability are not computed?
The reason
Right?
is
So-
that in the Frobenius norm, it becomes a Hilbert space module. So this is by definition things that fall under higher property T, because higher property T is talking about homology vanishing in Hilbertian modules. But when you talk about, for example, in the infinity norm, you get something which is more like a non-commutative at infinity space, which is in particular not uniformly convex, and all the Gaussian techniques, all the homological vanishing, classical homological vanishing techniques break down. So it's still open whether it vanishes, but it, like, that's another front you can attack it. It's still unclear. Like maybe Uwe and Wollmann can do it. That would be amazing.
So thank you very much.
Thank you.